Now, I told you at the beginning of this chapter, this is one of my favorites because we see so many applications of electromagnetic induction in our everyday lives. So let's take a look at some of those applications. Let's start with wireless charging of your phone. We know that creating a changing magnetic flux through a coil of wire induces an EMF in that wire. So we don't have to plug into the wall to get the EMF, to get the voltage we need to charge the battery. We can take the phone and set it on top of a coil of wire that's creating a changing magnetic flux. And if the phone has a coil of wire built into it that can take the changing magnetic flux and convert that into an EMF, into a voltage that will charge a battery, we're done. So your phones these days have some kind of a coil around the back. You can sit it on top of a wireless charger. The wireless charger plugs into the wall. The wall is AC, alternating current. So the current goes one way and creates a magnetic field in one direction, and then it flips and creates a magnetic field in the other direction, and the magnetic field is constantly changing. It's always changing. It's going up, it's going down, it's going up, it's going down. And if you put your phone over it, that changing magnetic flux through the coil built into the phone generates an EMF, a voltage, and that EMF can charge a battery in your phone. It's even more important in an electric toothbrush because they're used around water. And you don't want to have exposed electrical leads at the bottom of your toothbrush that connect to an electrical connection in the base for charging the battery, because those exposed electrical leads could be shorted when they get wet or when you're touching them with wet hands. So you have it all enclosed. There's no electrical connection at the bottom of that toothbrush, but it sits very nicely into the base. And the base is a coil of wire that plugs into the wall. And in the bottom of the toothbrush, there's a coil of wire, and those two made up, and the changing magnetic flux created by one coil causes an induced EMF in the coil in the toothbrush, and that voltage that's generated charges a battery in there. Another interesting application is the induction cooktop. As you can see in this picture, the stove does not get hot. The cooktop does not get hot. The pan gets hot. So here they have a frying pan that's cut in half, placed on an induction cooktop. The frying pan is hot. They've broken an egg over it. You can see the part that's on the frying pan is cooked. But the part that's on the cooktop is raw. It is not cooked because the cooktop remains cool. What's inside that cooktop? A coil of wire that's generating a changing magnetic field. That changing magnetic field causes currents to flow in the frying pan. And those currents cause it to heat up a little bit. But that wouldn't be enough to cook on. It does get hot, but it wouldn't be enough to fry food. If the frying pan is also ferromagnetic, the domains flip every time the magnetic field changes, as we've talked about in earlier videos. The domains flip, and the magnetic domains will point up, and then the external field causes them to flip and point down, and the flipping of the domains actually generates a lot of heat inside that frying pan. And it gets very hot, and you can cook with a lot of control. So they make very good cooking appliances. Another example is the ground fault circuit interrupt protection that we see on the outlets in our kitchens and bathrooms. Any place where there's water. Also, garages tend to have these GFCI outlets. And the reason is that if you get a shock, the circuit breaker in your house is not there to protect you. The circuit breaker in your house is there to protect your house. And if enough current flows through you to trip the circuit breaker that protects the house, it's too late for you. Yes, that would be bad news for you. So these point of use protectors. The protection is built right into the receptacle, and they trip very quickly because they detect very small current differences in what's going to the appliance and what's coming back from the appliance. We know that current should not get used up in a device. Whatever goes in one side should come back out the other side, unless the current has found an alternate path to ground, like through a person. So how does it work? Well, we've got two electrical wires labeled 1 and 2 here in my drawing, and they go to our device. Maybe it's a blow dryer, maybe it's an electric razor, maybe it's something else. And if the device is working properly, whatever current goes in comes back out. So there should be no net magnetic field around these two wires. One of them is producing a magnetic field that goes one direction, call it clockwise. The other one is producing a magnetic field that goes the other direction. And they should cancel out. There should be no net magnetic field around these two wires because they're both flowing the same current but in opposite directions. Well, if one of them has more current than the other one, if the current going to your device is more than the current coming back, that's a problem. It's found another path to ground, probably through you. And so what happens, we get a small magnetic field forms around these two wires and some kind of a circular path around these two wires. So we get this circular magnetic field. Well, it would be hard to detect that. It's a small magnetic field. So what do? We put an iron ring around those two wires. And when the magnetic field forms, the domains align and it intensifies the magnetic field and magnifies its effect. And we have a coil of wire running around that iron ring. So if we get a magnetic field that forms, normally there's no magnetic field through that coil of wire. If we get a magnetic field that forms, all of a sudden that change, right, from no magnetic flux to magnetic flux causes an EMF in the wire, and that immediately shuts off the flow of current through the device. And another application we see is motors and generators. Where would our lives be without those? Generators create the electrical energy we use, and they can create energy because we put mechanical work in and we get out electrical energy. Sometimes the work is done by water, the potential energy of water at a high place going to a lower place, like behind a dam, turns a coil of wire in a magnetic field and it produces electricity. Sometimes we burn coal to boil water, and that steam turns a coil of wire in a magnetic field, and we get electrical energy. Sometimes we use solar power. This image is from the world's largest solar power plant, at least it is today. It's in the Mojave Desert in Southern California, and it doesn't work on photovoltaic panels like the solar panels you see on people's houses or the ones in the foothill parking lot when you drive around campus. Those are mirrors, and they're concentrating the light from the sun onto the top of this tower, and it's heating up a fluid that's boiling, turning to steam, and that turns a coil of wire in a magnetic field, and that generates electricity. So let's talk a little bit more about motors and generators and how they work. In a generator, we're turning a coil of wire in a magnetic field. In this case, my magnet is set up, so my magnetic field is pointing to the right. As we turn that coil of wire, the magnetic flux is going to change. If the one side is connected to a metal ring through what's called a brush, we have to be able to turn this loop of wire without wires getting all tangled up, right? So what we do is we create a brush, a metal brush, and it rubs inside of a metal ring, and that makes an electrical connection, and it can rotate all the way around, and there's no wires that are going to get tangled up. So there's one connected to one side, and there's another one connected to the other side. And if we measure the potential difference there and plot it, the voltage would change in time. And look something like this. It would be a sine wave. Let's take a look at why that is. Instead of looking at it from the side like this, let's rotate our view by 90 degrees and look down from the top. If we're looking down from the top, and this coil is rotating in this direction, then the magnetic flux through the coil is being reduced, and it's going to the right. So a current will get set up to try to add more magnetic flux to the right. It will come up on this side, and it will go across the top and down on this side. This is a loop. We're looking down from the top of the loop. A little bit later, this loop has rotated, and now it's in this orientation. I'm going to use a highlighter to mark one side of my loop. So the side of my loop that I've highlighted in green is now located over here. And the magnetic flux is increasing. So a current is going to try to decrease the magnetic flux, which means it's going to come up on this side and go down on that side. So the current is still flowing the same direction through this loop. Let's take a look a little while later as the coil continues to rotate. Now this side is over here. It's continuing to rotate. So here it was still rotating like this, and now it's still rotating in the same direction. But now the magnetic field is to the right and getting smaller, so the current goes this way. The same as it was over here, right? Those are the same situation. The difference is that the current is going the opposite direction in that side of the loop because the loop has rotated 180 degrees. So what do I mean by that? I mean that the current was going up on this side and down on this side. Then the loop rotated 180 degrees, and it was still going up on this side and down on this side, but it's a different side of the loop, right? That's why we get this sinusoidal effect. The current goes one direction through the loop, then it goes the opposite direction through the loop, and it keeps changing directions. If I drew one more in this sequence, you can see that as the loop rotates, half of the cycle, the green highlighted side has the current flowing down, and half of the cycle it has the current flowing up. So the current is flipping direction in that loop as we rotate it. And that's what we show in this graph. When we plot the potential difference across that loop, we see that it flips, and that means it's driving the current in one direction and then in the other direction. So one of the things we like about AC power is that that's how generators work. We get AC naturally from a generator like this because of the way the electromagnetic induction generates that EMF. If we want to make a generator that generates DC, we can do that, but it takes a little doing. The first thing we have to do to make a DC generator is split that ring that the wire brush goes around. That's called a commutator. That connection there from the rotating coil of wire with the brush on it to that piece of metal is called a commutator. And if we split it down the middle and we connect half of it to one side of our voltmeter and half to the other side, like I'm showing here, as that loop rotates, the current will always flow in the same direction. It'll still be a sine wave, but instead of being a sine wave where we go positive, negative, it's a sine wave that's always positive. So we're halfway there. We don't have a constant voltage source. DC, of course, is a constant voltage source, but at least the current is always flowing in the same direction. Well, what do? We add another coil of wire, but this time we offset it a little bit from the first one. And that second coil of wire will produce a voltage that looks like this. And then we add a third coil of wire. That produces a voltage that looks like this. And maybe a fourth coil that produces a voltage that looks like that. And you add those together, and what do you get? You get something that looks very much like DC, a voltage that does not change in time, a direct current circuit. So you can make generators that generate DC, it just takes a little engineering know-how. Let's take a look at a motor now. In a generator, remember, we're putting in mechanical energy and getting out electrical energy. In a motor, we're putting in electrical energy and getting out mechanical energy. So we've got a coil sitting in a magnetic field. Let's run a current through it. Looking down from the top, if we run a current in this direction, that would be up this side and down the other side, what happens to our coil of wire? What's the direction of the force on this part of our wire right here? The force would be in this direction. The current's coming up out of the page. The magnetic field is to the right. The force is towards the top of the page. This is my magnetic field. And on the other side, we get a force that's in this direction. So what happens? There's a torque. This loop is going to rotate due to the torque produced by this current in the magnetic field. A little while later, our current has rotated. So let me mark one side in green. So our loop has rotated a little bit, and it is this orientation now. The current is coming up on the highlighted side of my loop. And what direction is the force? It's still in the same direction. So there's still torque causing this to rotate clockwise as we look down from the top. Now let's keep going. And if my highlighted section is over here, and I keep the current going in the same direction, what direction is the force? It's still in the same direction. So what just happened? Now my torque causes the loop to rotate in the opposite direction. So my loop will rotate half a turn, and then it'll flip and rotate half a turn, and let's go back and forth like that. Is that going to help us with the motor? No, we want it to keep going. So what do we have to do? We have to flip the current. Every time the loop goes around halfway, we have to flip the direction of the current in order to keep the loop going in the same direction. Well, we can do that a couple of ways. We can use AC power to run this motor. AC power, the direction of the current keeps flipping. So the potential is one direction, driving the current one direction. The potential flips, driving the current in the other direction. We can do it that way. Or we can use one of those split ring commutators that we talked about for generators, and it will end up flipping the direction of the current in that way too. So we can run a motor with AC power, just like we used a generator to generate AC power, or we can use one of those split ring commutators with the DC power, like a battery, and that will cause the motor to rotate and keep rotating also. So we can make motors work with both AC and DC power sources. Let's take a look at this video demonstration with motors and generators. This is a generator hooked up to a little light bulb. In a generator, we put in mechanical energy and get out electrical energy. Now I'm going to hook this generator up to a motor. A motor takes in electrical energy and puts out mechanical energy. On the left is the generator, and the electric energy is going to go into the motor. Oh wait, no, this one's the generator. Which one is the generator and which one is the motor? Now if I just have a generator all by itself, and the leads aren't connected to anything, so the generator can't create a current. It's an open circuit. Look how easy it is to turn that wheel. But if I connect the leads together so the generator is creating a current, there's a path for the current to flow on the output of the generator. Can you feel how hard that is to turn? It's very difficult to turn that generator. Disconnect the leads. Easy to turn. No resistance. Connect them together so the generator is actually generating electricity. And it's very hard. We have to do a lot of work. We have to put energy in to get that electrical energy out. As you saw in the video, I was using a hand crank generator to turn a coil of wire in a magnetic field and generate electricity. But you also saw that a generator and a motor are basically the same thing as far as physics is concerned. Now, in real life, they're designed slightly differently to optimize them for what they're designed to do. If you're designing a motor, you optimize it to be a motor. If you're designing a generator, you optimize it for that. But as far as the physics is concerned, they're basically the same thing. We put in mechanical energy into a generator and we get out electrical energy. We put in electrical energy to a motor, we get out mechanical energy. The second part of that video demonstrated how regenerative braking works in electric and hybrid cars. In an old-fashioned car, a gasoline-powered car, the car has lots of kinetic energy when it's moving down the road. And brake pads squeeze a brake drum and through friction slow your car down. So all that kinetic energy of your car is just dissipated into heat, heating up the air around your car. It's wasted. But when you have a regenerative braking system, you're driving down the road and the generator is not hooked up to anything. So it's easy to drive down the road. It's not costing you any energy. And when you want to stop the car, the generator gets connected to a battery. And when you do that, you get that, it's called a back EMF. It takes a lot of extra effort to turn that generator when it's generating. And because of that, it slows your car down. So the car, because it's turning that loop of wire in a magnetic field, generating some electricity that's being harnessed and stored in a battery, it slows your car down. So some of that kinetic energy becomes stored in a battery as chemical energy. Then when you go to start up again, you can use that energy to get your car moving again. So you're not wasting that energy every time you stop your car. Regenerative braking.